topics globally. So what I'm going to show you today are different possibilities in energy saving in the brewery. I will start with very simple solutions and going more sophisticated up until to a program that we set up a couple of years ago already, which can be rather considered as a kit with different energy saving measures. But let's start from the very first beginning. Just a second. Here we go. So what are the three, in our opinion, what are the three pillars of sustainability? And again, that is not only for our work lives, that's also a matter of our private life. We strongly believe that lowering consumption in general is the most important thing we need to consider. In our private life, switch off the light when you leave a room. Maybe you can reduce the temperature or increase the temperature in your case of the aircon, for example. When it comes to Europe or to Germany, we maybe can decrease the temperature from our central heating system. All of these have influences on saving energy. And that's also a matter in the brewery. So lowering the consumption should be, of course, from the very first beginning, one focus. Can also be not only on energy, but for example, on water consumption. Don't leave your water taps open too long when you do floor cleaning or something like that. Of course, new technologies play a major role in that one. We have a steady improvement of our technologies in all the fields in the industry. When it comes up in the brewing section or in the filling and packaging section, but even in the logistics sections. We can think about heat recovery systems, what I'm talking about today, and improved system design, whatever. Then, of course, the utilization of residual materials like wastewater recycling. Wastewater recycling is quite an interesting point when it comes up to biogas production. The biogas can be, for example, reused in your boiler system. Utilization of spent grains. That is something I will also highlight today. That's a really interesting point. Unfortunately, the technology is not as far as we would like to have it to be, and consumption, conversion of residual materials. And then, of course, if we cannot reduce the energy, maybe we can replace the primary energy by alternative energy, for example, by biomass, wind, solar energy, hydropower. There are several measures that's getting more and more important in the industry, but also on your private sector, especially when it comes up, for example, to solar energy. So what I would like to show you today, what I mentioned before, is to start in a very easy and simple, also simple to retrofit energy recovery possibilities, and then going a bit more into more sophisticated technologies. So the first one would be the energy recovery from the wort boiling process to simply heat up hot water. The second one would be also the energy recovery from the wort boiling process to an energy storage tank, and not only recover or heat up hot water, but also to reuse the energy in the brewing process to heat up wort. The third point will be our Aquitherm system. That is a more sophisticated system for new breweries mainly, but also for small breweries. We use this in our 50 to 100 hectoliter breweries as well. Very interesting system. And as a last point, I would like to give you an outlook what the future might bring or will bring. That's our so-called Brunoic. That is we started as a theoretical model of this Brunoic system, but meanwhile, lots of these different measures you will see here are being implemented in breweries already. So first of all, the brewing process itself requires a high demand of especially thermal energy. And this thermal energy, about 25 to 35% alone, are being used during the wort boiling. If you don't do any energy recovery here, it's just simply that you evaporate over the roof. Yeah, you don't collect energy back. And that is in the end a pity, yeah, because you can use this hot vapors in terms of heating up water, water for hot water production, energy storage, hot water, whatever. Further to that, it's of course a reduction of, or hand in hand with that goes a reduction of the evaporation rate in general. Rod White yesterday said something about that. I'm going to come back to this evaporation rate later on. So you should consider also to reduce the evaporation rate in general, or at least have a look at your evaporation rate, because the more you evaporate, the more energy you use, and the more you treat your wort on a thermal process. You can detect this with the TB set value, for example, that you have a certain stress on the wort. So a gentle boiling is also a benefit, of course, to your wort quality. Maybe at that point, before we go to the next slide, Charles, maybe you can come up with the next question at the poll, which is quite interesting. Here we go. So Rod yesterday was talking about the evaporation rate already, and the evaporation rate is quite an important factor in the complete energy recovery. And what I would like to know is what is your current evaporation rate? Is it something that you have never measured before? Is it 4 or less than 4%, or rather 6, 8, or more than 8%? Have you ever measured that one? That would be very interesting. So let's see. Do we already have a result here? Okay, so what I see is very good. The don't know was not ticked once. That's really good. And 8%, I would say, yeah, with 50% counting for the 8%, or even more than 8%, is quite a high number. Okay, that's interesting. I will show you now what is the influence of the or what is the average evaporation rate we are looking for normally. So what you can see here is a very simple path for decision making, how and where to reuse your energy. What you see over here on the left-hand side is that we normally calculate our systems with 4% of total evaporation. With this 4% of total evaporation, an energy recovery system is always in a balance, so it's at an equilibrium. Rod yesterday was talking about less than 4%, and yes, that is possible in general. With a reduced evaporation rate, of course, you also reduce the thermal energy that you require. On the other hand side, you always need to have a look at the qualities of your beers as well. Rod was mentioning that as well. So I quickly put in another slide just to have a short excursus on that one. It's the DMS as an indicator for the wort quality curves that you see here. So during the wort boiling process, which is this part, the wort kettle part, you reduce the DMSP, which is the magenta colored curve, and you reduce the DMS. During the wort whirlpool time, you still reduce the DMSP, the DMS precursor, but you don't evaporate anymore. And that means that you have an increase in DMS. And here you need to be careful. If you reduce your evaporation rate too far, you might have an influence on the quality of your beer. So a reduction of the evaporation rate should always be seen on the one hand side from the energetical point of view, but on the other hand side, of course, because it's your product, you need to sell your product, of course, from a quality point of view. So that was just a short excursus. So the first question is, are you using primary energy to heat up a hot water? So warm water for the brewing process. If so, is your total evaporation less than 4%, what is not the case in the poll, what we have seen before? You could recover the water for heating up warm water. If it's equal of more than 4%, you can use an energy storage tank or an energy storage system, and at the same time, maybe even heat up hot water. If you don't use any primary energy to heat up hot water, the same points here again, less than 4%, more than 4%, you can always store the energy in a energy storage tank. Yeah. How does it look like? The very first and most simple solution, which is also easy to retrofit in your breweries, is the production of hot water out of the wort boiling process. Yeah? What you need here is a so-called vapor condenser. The vapor condenser is running counter current or in counterflow the vapors against cold water. The cold water is being heated up and stored in the warm water tank, what you can use for the next brew for mashing in, for example. So that is the most easiest energy recovery nearly everyone can do in the brewery or retrofit in the brewery. Some of you who are operating breweries, for example, in closed buildings, in a restaurant or something like that, already have the cooling jacket, as you don't or cannot have the vapors inside your room. You should not have the vapors inside your room, so you cool them down to condensate them. Here at that place, you can also consider a heat exchanger, so the vapor condenser. That is the most easiest thing to recover energy and reuse it as hot water. A bit more high sophisticated then is an energy recovery system. What you see here is the two water tanks, the warm water tank and the cold water tank, and besides that, an energy storage tank. The energy storage tank is a closed circle, so you don't use this water for the brewing in general. It's just a heating medium. So you're still collecting energy from the vapor condenser, but this time not from the cold water tank, but from the colder part of the energy storage tank, so from the bottom part. It means you have about 78 degrees colder water, and you heat it up in a counterflow in the vapor condenser and transfer it back to the upper part of the energy storage tank. It's a stratification tank in the end. The temperature layers build up themselves because of the different densities in the upper part at 96 degrees. These 96 degree hot water you can reuse at a lauter wort heating system. So the wort that's being collected from the lauter tun is being transferred to the wort kettle in a counterflow to the 96 degree hot water. That means you're saving already the energy heating up your wort from 74 degrees, 76 degrees from the lauter tun to nearly 92 degree, 94 degree. So all of this energy, which you normally use as primary energy, you can use here recovered energy. That gives you an enormous saving already. That is, for bigger brew houses, state of the art already, and done quite often. Also, this installation or the setup can be easily retrofitted in the breweries. If you evaporate more than 4%, you can even use the surplus energy to still heat up hot water. So the complete system in general is in an equilibrium if you work with about 4% of evaporation. So the rest of the evaporation you can use for production of hot water. In some breweries, it's not really needed because if you have a day-to-day production, you normally have a surplus of hot water. But maybe you have a different kind of production, like soft drinks, for example, where you need hot water, or anything else where you can just use this hot water as well. So the next one would be coming to the Evaporation system. That's a bit more high sophisticated system. We also use this one in our smaller breweries, like I said, starting from 50 hectoliter onwards. And that is a next step in the energy recovery. In the end, you have seen this slide before for the recovery of energy from the wort boiling process. In this case, for the Evaporation system, we also collect energy from the wort cooling process. Because the wort cooling process is, again, an exchange of different kind of temperatures. You need to cool down the wort. That means you have about 98-degree wort coming out of your whirlpool, and you need to cool it down to your pitching temperature. Let's say 10-degree or 18-degree, depends on the yeast you're using. And also this energy can be recovered, and that is what we are doing with the Evaporation system. It's again another step in saving thermal energy, fossil fuels. Very interesting also the other aspects, especially the reduction of energy peaks in the boiler plant. In a normal brewery, it might be, or quite often it happens, that the wort boiling and the meshing, the heating up during meshing, take place at the same time. So I have very high peaks in the steam consumption, not an average consumption in the boiler, but a high peak. And if I'm not going to use any steam anymore during the meshing process, I can reduce those peaks and use smaller boiler systems. Besides that, we have a lower demand for ice water, so we're saving electrical energy over here, and a lower heating medium temperature during the meshing process has definitely positive aspects on the quality of the worts as well. So how is this system working like? What you see here are the media flows of a normal meshing or a normal brew house. We start with the meshing in. For the meshing in, we do need hot water. For the meshing itself, to reach the different temperature rests, we need to use steam. Then we have the lautering process with the sparging water. We have the heating up to 92 degree, which can be done with the normal energy recovery. So during the boiling, we recover the energy, we reuse this energy for the first heating up. So we only have the steam demand being used for the boiling itself. With the Evaporation system, we don't use steam for heating anymore at the mesh tun. As you can see, we don't have this red arrow anymore using steam, but we are collecting energy from the wort cooling process and store it in an energy storage tank and use this hot water for the meshing. So the steam jackets at the mesh tun are not operated with steam anymore, but with hot water. You can see this in the next slide. Over here, you see a diagram. You can see on the right-hand side the classical energy recovery. So we have the holding vessel with the Lauterwort heater and the vapor condenser, where we already collect the energy from the wort boiling process. And this energy is being stored in this energy storage tank, which you can see on the left-hand side in the green square. So we use the colder part of the energy storage tank, the 67 degrees water, 76 degrees water, going to the vapor condenser, collecting the energy here, being heated up and transferred back to the energy storage tank. As an additional step, we use the same energy storage tank, also use the colder water in the energy storage tank, and this is now connected additionally to a first stage at the wort cooler. And we collect here the really high energy and transfer it back to the energy storage tank. The storage tank for this system is a little bit bigger than the one for a classical energy recovery. And now we are using the hot water on the one hand side for the Lauterwort heating. That was classical energy recovery. On the other hand side, we use the hot water also for the meshing. That means the steam or the heating jackets are not being operated with steam anymore, but only with the hot water. And here you can also see that we don't or can reduce the peaks in the steam demand at the steam boiler. Yeah, so there is not any steam anymore at the meshing group. This can of course also be done if you have a decoction method. Yes, if you are going up to boiling temperatures, we need to consider a small booster here because the temperature in the energy storage tank is at about 96 degrees. If we need to go up to boiling temperature, we need to have a small booster system to heat up the water higher than 100 degrees to reach boiling temperatures. But in the end, still we recover a lot of energy over here that makes the system also able to run with a decoction method. What you see here is a graph of the peaks at the steam boiler plant itself. As I mentioned before, we don't have those high peaks anymore because the heating of the mesh and the heating of the wort kettle is getting along at the same time. We only have left over in the brew house the heating of the wort kettle. Therefore, the total size of the steam boilers can be reduced, which is, of course, an impact on the investment. Yeah? What are the energy savings for these systems? That is quite a high number, especially on the thermal energy. If you compare to a brewery system or a system that is operating without any energy recovery, we can use up or save up to 55% of thermal energy. And that's really a high amount. Yeah? If you're going to calculate this one into the gas, the oil, the diesel you're using, so that is quite a high number. Depending on where in the world we are going to set up these systems, we can reach return on investments here of approximately 1.5, 1.8 years. So that's also a really quick and fast return on investment. Besides the thermal energy, we are of course saving also on the electrical energy, mainly when it comes up to the wort cooling, because we have this first wort cooling stage being used the hot water from the energy storage tank, so also the cooling plant can ramp down. And of course, we have the reduction of the thermal peaks, like about 50%, up to 50%, depends on what kind of system you're already using. So that is, in my opinion, quite a high number and should be worth to think about for everyone who is planning a new brewery. As I said, also for smaller breweries, this system is available, and for sure is worthwhile to think about. Not only, as I mentioned in the very first beginning, in perspective of cost savings, but for sure also an aspect on sustainability in general. What I would like to briefly show you now, I will not go into too many details here, is our Brunoic system, which in the end started a couple of years ago as a theoretical calculation with different kind of measures for energy savings. In the end, it's a collection of energy saving measures, which meanwhile were implemented in a lot of breweries, not all at once, but depending on the demand of the breweries, only some of these parts of the Brunoic were implemented, and it should give you rather a certain kind of or should be considered as a certain kind of brainstorming, because it shows there are a lot of things you can do in a brewery, also in existing breweries, in order to save and reduce energy and energy costs. So the theoretical calculation, or the idea, is about this Brunoic to have a complete self-sufficient and CO2 neutral brewery by mainly reusing the waste products. In this case, it's the spent grains with a major focus being reused, or the calculation is based on reuse the spent grains in a biogas plant. There is a certain but. We know that it's not so easy, and these plants are not really available on the market so far, to degrade all the spent grains like we would like to have it. It takes a very long time, so these plants need to be enormously big, especially when it comes up to bigger breweries. But the theoretical reuse of the thermal energy is given. So that would be the general concept. You can see here in the upper part the brewery itself. The brewery is producing spent grains. We would use some of these spent grains as we are doing already now for cattle feeding. And some of the spent grains, like 80% shown here, for the biomass conversion, or conversion of biomass to biogas. That is what I said. The biogas plant itself for bigger breweries is not yet available. But on a calculatory base, we would use this biogas for a combined heat and power plant, what you see in the lower right-hand corner, and directly also for the boiler plant. The complete brewery will be operated only with hot water from one central energy storage tank. The combined heat and power plant, of course, will serve the utilities together with solar power, and the electricity also will go to the brewery. So all in all, on a calculatory theoretical base, this is in the end, self-sufficient brewery producing even more energy than that is going to be used or can be used in a brewery. To have a smaller starting step, we reduced the complete system by the biogas plant, and you can see here in the center there is a city gas, but still the same setup can be used. And what you see right now here is already being implemented in breweries as well. So operating with city gas, the city gas is serving the boiler plant as well as the combined heat and power plant. So we have the central energy storage tank, and all of this operates the brewery. So that is already proven that it's working out very well. The heart of the brewery will be a water tank, a hot water tank. So what we call a low temperature brewery with not too high water temperatures, using these different kind of hot waters in the different layers in different stages in the brewery. That means we can use it for the meshing, like the Evaporation system we saw before, but as it is a pressurized system, it could also be considered for wort boiling. We can use it in the filling and bottling area, wherever thermal energy is being used. We would operate the complete brewery with a combined heat and power plant, and in best case with a biogas boiler. With all these energy saving measures, especially for this more sophisticated, it is important that you run permanently your brewery. So if you are working or consider working with an energy storage tank, doesn't matter if it's now the Brunoic or an Evaporation system or a classical energy recovery, you always need to have a constant and steady production of energy that you are going to reuse. So your production should not, or your production schedule should not be like brewing all your brews from Monday to Wednesday, but to spread your complete production schedule over the complete week, so that you always have a steady feed of energy to the energy storage tank. So that is an important point when considering to invest in whatever energy recovery system. So this will not really work out when you only do 2 days or 3 days of brewing. I'm quite sure that the presentations will be shared later on. So what I will not go into detail of all these collection of different possibilities. So this skit for the Brunoic, I think that would be too long now. But you can see here the measures that we have taken into consideration for a fully balanced brewery. That is, of course, mainly focusing on larger breweries, like, for example, high gravity brewing throughout the complete recipes and process. Gentle wort boiling system. Here you can see also the evaporation rate again with about 2.5%, because the energy storage system is in an equilibrium of other heat sources, like the combined heat and power plant, for example. That is for the Brunoic. Continuous batch process, that is what I just mentioned. You need to have a steady production over the complete week. Other measures are the Evaporation system that you have just seen, the energy storage unit, so the storage tank of hot water, and the low temperature brewing operated with low temperature hot water. There are several other measures, energy saving from coolant supply, solar power, solar heat, ice water production, which is quite interesting. Combined heat and power plant is something that is coming up more and more. We get more and more requests of that one, because from an investment point of view and also return on investment, that can be very interesting depending on your costs of energy in the country where you're operating your brewery. So besides the different components, technical components, what we also offer is, of course, our knowledge. So what we are doing is providing energy audits. So if you would like to optimize your brewery, you can give us a call. We can have a look at the brewery. We have a look at the recipes, at your evaporation rate, of where can you use what. It's a matter, not only a matter of the process itself, so the production of wort, but also, for example, checking or counter checking your CIP times, your CIP temperatures, chemicals, and so on. So there are a lot of different possibilities in terms of saving energy, and we really would be happy to support you in that one, because we really see that the sustainability in brewing is our future. Maybe one sentence to that one. We are going to plan to build all our brew houses in the future, starting from next year, with our Evaporation system. At least if you're not going to implement the system from the very first beginning, that the vessels, especially the mesh tun, is ready to retrofit afterwards. So our focus definitely here is on sustainability during the next years, and we hope that our customers, our brewers we have worldwide, have the same vision like we have. So if you have any questions, please feel free to drop me a message, give me a call, send me an email, whatever. Can send me a WhatsApp as well. That's not a problem. Thank you for your time here. This has been the last session of today, or of the C-Brew Conference 2021. I'm very happy that I had the chance to speak here. Thank you for your time and for listening, and open for any questions and answers.